Hello everybody. This video is for MME 2305, Material and Energy Balance. I'm the instructor, David A. Robertson. I'm a professor here at UTEP. I can be reached at drobertson@utep.edu should you have any questions, or if you're in class, you can come ask me questions in class. The purpose of this video is to familiarize you guys with some topics and some techniques that will be very, very helpful when we get to the material balance portion of the class, which will come up quite shortly. The four main topics we're going to talk about today are flow rates, mass, mole, and volume fraction, molecular weight, and finally, concentration. Boom! Okay, we got camera firing on all cylinders, sort of. The rates we tend to care about in this class are mass flow rate, volumetric flow rate, and molar flow rate, okay? And you know it's a rate because of the dot. So a dot signifies a rate, okay? So in other classes, you may be given epsilon dot, and so that would be strain rate, and that would be in millimeters per minute. Okay, so strain rate is given in terms of millimeters per minute. So logically, you can assume that mass flow rate is basically given in units of mass over time. Volumetric flow rate is units of volume over time, and molar flow rate is units of moles, or number of moles per time, rather. So let's start off with mass flow rate. M, okay? So example units of mass flow rate would be grams per minute, kilograms per hour, kilograms per second, pounds mass per hour. We could do grams per day. Any unit of mass over unit of time would be essentially a mass flow rate. Let me adjust the camera a tad because it's not showing us what we want, and my chicken scratch isn't doing people many favors. Okay, so mass flow rate. So let's take an example of a time that we would be messing with mass flow rate. Okay, we would have maybe titanium dioxide would be a good example. And let's say we work in a paint factory, so we're flowing some titanium dioxide into some sort of mixer. We're making paint. Just as kind of an aside, titanium dioxide is the pigment that makes paint white. Before people used titanium dioxide, they were using lead, which is kind of hazardous to human health, so we no longer use that as a society. If you take an air sample in like a general neighborhood, you're more than likely to find titanium dioxide in your air sample. If you did that in the 1960s, you would actually find lead oxide, which is a little concerning. Okay, so we have titanium dioxide, and we have a mass flow rate, M. And let's just say we have a mass flow rate of 100 grams per hour. And we're asked to find the volumetric flow rate. Or let's just put what is the volumetric flow rate? Well, we see that mass flow rate is given in terms of mass per time. Let's take a quick look at volumetric flow rate. So volumetric flow rate is units of volume. Per units of time. So an example of that would be centimeters cubed per second, liters per hour, meters cubed per minute. Excuse me. We could do centimeters cubed per day. So any unit of volume over unit of time. So we want to get from mass flow rate, which is units of mass per unit of time, to volumetric flow rate, which is units of volume over unit of time. And it just so happens the material property of density can be used as a conversion factor because density is mass, density is mass over volume. So an example unit of density is grams per centimeter cubed. Okay, so we take a look at our little problem we've made up here. We're flowing 100 grams per hour of titanium dioxide into this paint mixer. And we want to know what the volumetric flow rate of titanium dioxide is. So we start off with 100 grams per hour. We're using our railroad track method in this class. And if you've not seen the video, I implore you to go take a look, especially if you're taking this class. So 100 grams per hour. And for bookkeeping purposes, I should have put titanium dioxide in there. So 100 grams per hour of what? Because as the problems get more and more complex in this class, bookkeeping is essentially the key to survival. And we'll go over that a little bit more in future lectures and videos that accompany this class. So it just so happens that the density of TiO2, according to my handy dandy research I painstakingly performed before making this lecture, this is really, really bad notation. So density, here, just excuse this. Density of is 4.23 grams per centimeter cubed. All right, so we want to make sure our grams cancel because we want to end up with units of volume per units of time. So if the density of titanium dioxide is 4.23 grams per centimeters cubed, we want to make sure our 4.23 is in the denominator part of this calculation. And we want to make sure that centimeters cubed ends up on top. All right, so our mass flow rate is 100 grams per hour. We want to end up with a volumetric flow rate. So the units we want are centimeters cubed per hour. So let's make sure this is going to work. So yes, grams cancel. So if I divide 100 by 4.23, let's see, what do I get? I get 23.64. I believe in class we agreed just to report the first decimal point, so I would round up, and we're below 5, so we can just go ahead and report 23.6. And we're going to do centimeters cubed per hour. And always when you do some sort of calculation to note where your answer is. And I probably should have put equals V, but here, we'll just put it up there just for good bookkeeping. Dot. So we have our volumetric flow rate now of 23.6 centimeters cubed per hour. Now, the next flow rate that we're interested in is molar flow rate. Okay, so N with a dot on top is number of moles per time. Okay, so let's take the example of aluminum. And in some countries, it's aluminium with a different spelling, but in the United States, it's aluminum. So if you look at my handy dandy periodic table provided by EDAX, makers of fine X-ray detectors, and you can't really read it. My camera's not the most premium camera. So you can look it up on Google or if you have your own periodic table, but the atomic weight of aluminum is 26.982. Now, most of you, if not all of you, have taken chemistry at one time in your life, and you're probably told that this means 26.982 grams per mole. But in this class, we deal with other types of moles, okay? So it is implied that since our units are grams, this is in fact a g-mole or a gram mole, to be more precise. Okay, so our units of mass are in grams, so the accompanying unit with the mole is gram mole. So it's implied, particularly in those chemistry classes, that it's a gram mole. In this class, we also deal with kilogram moles, and we also deal with pound mass moles. So we also deal with some imperial units in this class. And so it just so happens that the atomic weight of aluminum is 26.982. There's 26.982 kilograms per kilogram mole. And this sometimes blows people's minds, but there's also 26.982 pounds mass in a pound mass mole. Pound mass mole of aluminum. And I should probably be putting aluminum so we can practice bookkeeping from the get-go in this class. It's a good skill to build. So I know what people are thinking. They're thinking, man, well, what about like unit conversions? How can we have the same number assigned to a gram mole, a kilogram mole, and a pound mass mole? Well, atomic weight, molecular weight comes in, the unit conversion comes in when we're actually doing calculations, okay? So let's make up a quick calculation just so you guys can have an example. So let's say we have 1,000 kilograms of aluminum, and we want to know how many pound mass moles this is. Okay, all right, how many pound mass moles is this? So we'd set up our handy dandy railroad track method that we should all be pros at least by the end of the class. So we want to start off with 1,000 kilograms aluminum. And it turns out we want our kilograms to cancel, and we know there's 26.982 kilograms of aluminum in 1 kilogram mole of aluminum. All right, so we know kilograms of aluminum are going to cancel out. If we performed a calculation now, we'd know how many kilogram moles of aluminum there are, but that's not what the question is asking. We're wanting to know how many pound mass moles are there. Well, the conversion factor between kilogram moles and pound mass moles is the same as converting a kilogram to a pound, okay? And so there are roughly 2.2 pound mass moles. Go ahead and put aluminum in 1 kilogram mole of aluminum. And so we want to make sure our units are going to cancel. So kilograms of aluminum cancels, kilogram moles of aluminum cancels. And so we're left with pound mass moles of aluminum, which is what the question was asking for. And so if I type the numbers into my calculator, painstakingly type it in, I get the value of 81.5 pound mass moles of aluminum. So very simple. And let me tilt the paper a little bit more. Let me cover again what I just wrote in case you guys didn't see it because my arms are all over the place and stuff like that. So we had 1,000 kilograms of aluminum. We wanted to know how many pound mass moles that equated to. So we set up our railroad track method. So we start off with 1,000 kilograms of aluminum. We know based on the periodic table that there are 26.982 kilograms of aluminum in 1 kilogram mole of aluminum. The conversion factor we use to go from kilograms to pound mass is the number 2.2. So we plug and chug and we get 81.5 pound mass moles of aluminum. So if you remember, we got onto the subject of different types of moles because we were talking about molar flow rate, okay, N dot. So if I go to another piece of paper, we can kind of recap a little bit. So molar flow rate. And that's the number of moles over time. So let's make an example using, again, our friend titanium dioxide. Titanium dioxide comes in two polymorphs, just a fun fact. Anatiz, I'm probably pronouncing it wrong, and rutile, which is probably the more common of the two. Someone may want to correct me on that. I don't know. So titanium dioxide happens to have a molecular weight of 79.866 grams per mole. And hopefully you can read that. So 79.866 grams per mole. Let's go back to our first problem where we said we had 100 grams per hour of titanium dioxide going into our paint mixer. So we'll kind of recap or redo this. So we had 1,000 grams per hour. Oh gosh, getting my capital letters mixed up. Excuse me. Going into a mixer. And we know since this is the mass flow rate, we want to know what is the molar flow rate. So what is the molar flow rate? Oh my goodness. Okay. Well, we know that mass flow rate is given in terms of mass per time. And we know that molecular weight is given in terms of mass per mole. So we can use molecular weight as a conversion factor to actually get from mass flow rate to molar flow rate, which is where we want to go. So let's set up our railroad track. Here, I'll pretend I didn't make a mistake. 100 grams per hour, goodness gracious me. And I keep forgetting to do the bookkeeping. 100 grams per hour of TiO2. The molecular weight of TiO2, so there's 79 grams of TiO2. And even though I'm kind of doing a bad job in this example, please start getting in the habit of doing good bookkeeping. So we have 100 grams of TiO2. We have 79.866 grams of TiO2 in one. We can do Gmol TiO2. And then we get the answer of 1.3. So there's 1.3 gram moles, and I probably should have put this up top. 1.3 gram moles of TiO2 flowing per hour, and that's equal to our molar flow rate. All right, so we've gone from mass flow rate to molar flow rate, and that's actually pretty simple. However, if we're given a volumetric flow rate, we probably can't do it with just one conversion factor. So let's take a look at this. I'm not a betting man, but I would think we would need probably two conversion factors to get from a volumetric flow rate to a molar flow rate. So let's make up a problem. So let's say we have 200 centimeters cubed per hour. And again, man, I'm sorry. Titanium dioxide, it's flowing. And we want to know what the molar flow rate would be if we have 200 centimeters cubed per hour flowing through. Okay, so we said on our mass flow rate problem that the density of TiO2 was 4.23 grams per centimeters cubed. And so if we're trying to get from a volumetric flow rate, so we're trying to get from a volumetric flow rate to a molar flow rate. So we're trying to get from volume per time to moles per time. There's some in-between step, or one in-between step we have to make. So first we have to go from volume to mass, and then from mass to moles. Because molecular weight, and maybe there's this type of data out there. I don't know if there is such thing as a volume per mole table or volume per mole chart. Perhaps there is. Maybe Google it and we can discuss it if you find it. But for now, I'm going with what I know in my head, and I know that molecular weight's readily available on a periodic table, And I know that density is a pretty easy value to find for stuff. So we're starting off with 200 centimeters cubed per hour. We know that the density of titanium dioxide is 4.23 grams per centimeters cubed. So the first thing we want to get rid of is centimeters cubed. So we can just put in 4.23 grams per centimeters cubed. We don't have to flip the unit this time like we did in the other example, so kind of pay attention to that. If you don't remember what I'm talking about, feel free to hit rewind. And we know our molecular weight of titanium dioxide is 79.866 grams per mole. So 79.866 grams, man, I'm doing this bad again, grams of titanium dioxide per gram moles of titanium dioxide. And technically, you should have put 4.23 grams of titanium dioxide in 1 centimeter cubed of titanium dioxide. So again, I implore you, keep the bookkeeping, kind of do as I say, not as I do. I tend to get in a rush when I make these videos and do stuff on the board. Maybe I need to take a couple of deep breaths before I do this stuff. So here we go. So let's see, let's do a quick inspection of what we're doing. So we have centimeters cubed of TiO2, cancels out. Grams of TiO2 cancels out. So we're left with gram moles of TiO2 and hours, and so we're left with moles per time. So that is the definition of molar flow rate. So let's plug and chug through our calculator. Feel free to calculate at the same time. I try to do the best I can punching numbers, but I have been known to make mistakes. So we have 200 times 4.23. If you want to pay attention to the intermediary step, see if you can actually see it. I got 846, and you can divide it now by the molecular weight of titanium dioxide. So 79.866, and I get 10.59, so we can round it up to 10.6. And again, feel free to follow along. 10.6 gram moles per hour. And we'll do TiO2, and that's the molar flow rate.